Okay, we're finally ready. Sorry about everything. So yeah, what will happen is we have. Can you hear me all right? Yeah. So we have half an hour before we're done with our usual class time. If you, I will stop the recording at that point. If you want to leave, just leave, and I will keep recording the class. Then you can see that online. I don't see any other way for us to work this out. So yeah, I need to open my class. Here we go. Yeah, of course, as usual, if you have any questions, just stop me. The idea is for today, this is going to be lecture 7. Lecture 7. This is going to be more on continuous functions. So the idea will be, well, essentially continuous functions. If you don't know what a continuous function is, you can't really decide whether a topology is good or not. I'm going to convince you of that today. So some things I want you to recall, kind of briefly. We have the Cartesian product of sets. So the Cartesian product, the idea here is, remember the finite case. So something like if you have two sets, x1 cross, let's say, x2, this is just pairs, a1, a2, where a1 is in x1, a2 is in x2. And that's the finite case, not very interesting, but more generally, if you have a family, xi, where the I is any element in an arbitrary index set, then we can define the Cartesian product of these xi's as the set. And now your tuples are going to be functions indexed by lambda, landing into, say, the union of all xi's. And what you want is a at point I, or at index I, you want it to be an element in the corresponding set xi. So the important thing here is, for example, when you're in the product of these two sets, you have two projections, P1, going from x1 cross x2 to x1. Here we're just taking a1 comma a2 to a1. Of course, we also have P2. I'm not going to say what it is. To x2. Here, your pair is going to a2. And in general, if you have an arbitrary product and you fix any index, so for any fixed index, let's call it j to distinguish it from I, we have what we call the jth projection, which goes from the Cartesian product of all xi's to your favorite xj. And here you're taking a function or a tuple A to its value at j, which we know is an element in xj. And what I'm saying this because I want to address this question. The question here is, how do we describe functions landing into the Cartesian product from some set x to the Cartesian product? So for example, in the case of just x1, x2, if you want to describe the function from some set x to x1, x2 times, usually what you need to do is you take some x here. So here f of x is going to look like something comma something, right? Because it's a thing with two coordinates. The first something sometimes we call f1 of x, and the other one sometimes we call f2 of x. So what I'm saying, instead of giving me a function, you need to just give me these two guys. So you need some f1 from x to x1 and some f2 from x to x2. How do we recover this f1 and f2 if we only know f? How do we recover these guys? Well, f1 F1 is just do F and then project. So F1 is just do F1, do F, sorry, and project with P1. And F2 is, well, these guys just do F, but project to second coordinates. And of course, you don't need the product here to be finite. You can do this in any other setting. So let's write that as a definition. So definition, I will say this is not topological so far. Notice everything here is just set theory. So let's take a function from some set X to Cartesian product. Any function. I'm going to define the jth, and let's say we fix some index j. We define the jth coordinate of f as the function. We're going to denote it fj, which will go from x to xj, and is given by. So here I will write how I like to write functions, and then I will clarify what I mean. So fj is go from x to the Cartesian product and then project. So here's your pj, here's your f. In other words, you can just say your fj is first do f and then do pj. So this is the definition. But probably it's easier to remember this. More schematic. And notice here, if you tell me what fj's are, you know what f is. So I won't say much, but this is really something we talked briefly about the category of topological spaces. So this is somehow telling you that the product is a categorical thing. I won't say much, but I will just say we don't know why. Fact, f is completely determined by these fj's. As is the case in the finite case. If you tell me the coordinates, you know the function. If you want to define a function, you only need to give me the coordinates. So both ways. Okay, that's kind of set theory, but now we want to do something topological. So before we go there, let's briefly recall. So last time I left you with an exercise about the box topology, but now let's go to the product topology. So the product topology, by definition, so let's denote this T-box, T-prod on the Cartesian product. So here I'm assuming each xi has a topology. We define it with a subbasis. So the subbasis is something I will denote by S, and that S is you take any open uj in xj, and that for any j. And what you do is you do pre-image under the jth projection. That's the subbasis. So what this means is in the jth coordinate, you have uj, all the other coordinates are the entire xi's. And now let's write our first theorem for today. This will be called the product topology theorem. So this is telling you why the product topology is a good topology. So I'm going to assume we have a collection of topological spaces, xi, and now let's fix ti, where I is an index in some index set. So assume these are topological spaces.
You answered my question.
Okay. Then the claim is, the first one is the product topology. So something that you want minimally, if you have a topology on the Cartesian product, the minimal thing you like is for all the projections to be continuous. These are very natural functions. If they are not continuous, maybe you need to change your topology. So the product topology is going to make all projections continue. But not only that, it's the smallest in the set theory sense, or the coarsest, making that happen. So it's the coarsest topology on the Cartesian product, such that all projections from the Cartesian product to xj are continuous. So it's the coarsest means that that's the smallest one as a set. If you have any other topology in which all projections are continuous, then it's going to contain the product topology. And the second claim here is if we have any topological space, and we have a function going out of that topological space x tau to our product space. Here I want to consider the product topology. That function is continuous if and only if each coordinate is continuous. If and only if the coordinate function fj from x tau to xj with tau j is continuous for all j. So I'm not saying why, but these two things are telling you that we know that we have the category of topological spaces, whatever that means, and we have this construction of products. This is telling you that product is going to behave well in this category if you consider the product topology. This is not true with the box topology. That was the example for you. The exercise for you. I will write that in a second. So let's try to prove one. So let's try to write a proof for one. So I'm saying the product is the coarsest topology doing something. So I first need to verify it does something, and then that it's the smallest one. So first I need to show that each projection here going out product with the product topology to my xj is continuous.
We want to show this?
Yeah, that's the first thing we want to show. Why is this true? Well, if we take an arbitrary open in the codomain and we compute the preimage, that's not only open here, it's a sub-basic set here. So absolutely true. In fact, given, let's call it uj in tj, what we know is that the preimage of that open under this function that we want to show is continuous. It's an element in S, which is of course a subset of T prod. Because T prod is the smallest topology containing S. And that's all we need to show. And that's what it means for Pj to be continuous. So that's for free. And now we need to take another topology. Let's call it T topology on the product, making the projections continue, such that each projection going out of xi with this T to xj is continuous for all j. And we want to show it contains T prod. So we want to show T prod is the coarsest, means T prod is inside this T, this arbitrary T. But since T prod is the smallest one containing S, I should say coarsest, but I'm using smallest to be clear, is the smallest one containing S, our south basis. Instead of proving this inclusion, instead of proving this, we just need to prove that S is inside this given T. Right? If you prove S is inside that T and T prod is the smallest one containing T, then T prod will be contained in T. So how do we prove this? Remember here, an arbitrary element looks like this. So we want to show each of these guys lives in T. But that's for free because this guy is continuous. So if you take an arbitrary uj, so pj inverse of uj in S, that's how elements in S look like. So here, j is an arbitrary index and uj is open in xj. That's an arbitrary element in S. Then this guy is in T just because our pj going out of the product with this tau topology to xj is continuous. If it is continuous, then preimage of open is open. So the proof is for free. And that's all you need to do for one. Any questions? Yeah.
So I just want to clarify, we want to find, we keep scroll up a little bit. So the goal is scroll up. So the goal is to find a open set U in TJ such that
No.
T inverse J of U is an S, is a subset of T product, and then we have its continuous.
No, but I don't have to find an uj. I have to prove, for example, when I want to, so what's the question about the first part or the second one?
Well, I think you kind of answered it, but because we can't find a UJ in the image, we have to look at the pre-image.
You don't need to find uj. You need to take an arbitrary uj open and then compute its pre-image or show its pre-image is open. And that's what we're doing, but you don't need to find uj. So that's all for part one, and then part two will be a homework assignment for you. So part two is telling you something is continuous if and only if each coordinate is continuous. That'll be a very fun exercise for you.
Can you go to where you define U? So I can
Where I defined the
you said U and then the pre-image of U. Then we defined that earlier or no?
like here.
How do we know that? Yeah, I don't know if we talked about it.
So here, what I'm taking is an arbitrary element in S. And arbitrary elements in S look like this, where you are fixing an index and taking an open uj in xj.
So it's the pre-image of an open inside of some topology.
Right. So this is, let me go up to the definition. This is how we define the subbasis for the product topology.
Which is, that's just a specific definition of subbasis.
Right. This is how we define the product topology. This is a subbasis. Oops, sorry. That's a subbasis for something, for some basis, and the basis that you get is called the product topology.
Okay, I see. And all topologies can have different subbases, right?
Yeah.
Okay. Yeah, so we're just using that definition down there.
I'm using this. I mean, not really using. What I'm using is if you're a topology containing S, then you contain the product topology.
Oh, S is a subbasis for your topology.
Right. That's what we call the product topology.
Yeah, that's the product topology. Okay.
Okay. So 2 is homework. And why am I even saying this stuff? Because last time, so example, this is not new. We've been here twice before. We have the function f going out the real numbers to what I denoted by r to the naturals. This means by definition, product of reals, how many times? 1 for each positive integer. And this function is given by, it's not any function, f of t. Here I will use coordinates, t forever. So I asked you to show, you showed the function, if you consider the standard topology on the reals, that's always the case, going to the product with the box is not continuous. The idea is well, actually, I showed this. It's not continuous because there is this very small open set containing 0, and the preimage is just the singleton 0, which is not open. And then I also ask you to show that if you compute f going out of the reals with the standard topology to r to the n with t prod, I ask you to show that preimage of a basic here is open here. And that's enough to show this function is continuous. That's one of the equivalences in the continuous function here. This one is continuous. I ask you to show this, and now we can give an alternative proof. Why is this the case? Well, since we have this topology here, it's enough to prove the coordinates are continuous. And what are the coordinates here? What are the coordinates? Jth coordinate evaluated at some t. What I need to do is I need to compute f and then project to my coordinates. But our coordinates are the same here. So this is t. So each fj from reals to reals, both have the standard topology, is the identity, which is trivially continuous. And by our theorem, if all the coordinates are continuous, that's what you will prove, then the function is continuous. And we're done. So this example is very nice because this is telling you there's a function for which all coordinates are just the identity. So as innocent as it could be, which is not continuous with the box topology, but is continuous with the product topology. And that's kind of telling you, maybe you want to go with the product. Yeah.
Yeah, so you just said it wouldn't work with the box, so the identity doesn't work. There's a mapping with the box topology.
What do you mean doesn't work?
Which part, if you were to replace product with box, which part of this would fall apart? Which part of this continuity proof would fall apart?
Well, the argument, you cannot use the coordinates argument because the coordinate argument only works for the product topology.
Just because of how we defined it.
Yeah.
Okay.
But mostly because of this theorem.
Is there a specific part where you're like, oh, here we take a subset or something, and we couldn't do this in the box because. Is there a point where that is clear?
I mean, the theorem is not true if you do box topology instead of product topology.
So,
And the reason why it's not true, it's the example, this example we have here.
so just like take it for granted. That it doesn't work in the box.
You have an example. You have this example.
Is that true because of this example?
Well, it's not true, and this is an example, an instance in which that's not true. There are more examples, but this one is one of them.
So what was the explanation for why that didn't work again?
Probably you need to go read last time class, but there's a very small open here.
I did have a question on that. We use the particular sets of -1/i.
Right.
Oh, yeah.
I, and you said that 0 is not open, and I didn't quite catch that.
So yeah, the argument is something like here in T box, you can take this box -1/i, +1/i over integers. This is open in T box. But when you do F inverse of U, we showed it's just a singleton zero. And I'm claiming this one is not open. And why is it not open? If a set is open and there is a point in the set, then you need an open interval around the set containing the set. Right? So it is not a neighborhood of 0. Of 0.0. And why is that? Because negative epsilon, comma epsilon is never a subset of 0. Because you have stuff there. So singletons are not open in the reals. You need for each point, you need an open interval. So yeah, the moment you are open, you're very infinite. More than the integers. Are we okay? So that's the reason why this function is not continuous with the box topology. Okay. So that's one thing. I think this is a very good argument why the product topology is better, at least from a categorical point of view, whatever that means. Now, the next thing I want to discuss today is, at least very briefly, homeomorphisms. So the idea here is, if you've done a linear algebra class, you know what a linear isomorphism is. Well, this is the topological version of that. So definition 2 for today. I will say that a function, let's call it f, from x to y, between topological spaces, so I have x and y topological spaces and a function between them. I will say that function is it's a homeomorphism So let's try to guess. This should be the topology version of a linear isomorphism. So we say that f is a homeomorphism. Instead of linear, we want to say continuous. So if f is continuous, and what else? Right, we want it to have an inverse. So f is continuous, f is invertible, That means bijective. Are you more familiar with invertible or bijective?
Same.
Okay, I'll say invertible. And the inverse, which is a function from y to x, is also continuous. And that's not something you need to say in linear algebra. So I will not write it here. I will upload that to my notes. But in linear algebra, if you have a linear function that's bijective, then the inverse is also linear. That's not the case here. So let me just say note, f can be continuous and bijective without the inverse being continuous. So I will give you a very trivial example of this, and then we'll work towards a better example. So example. The example will be very naive. I will take any set, fix set x, and I will assume we have more than one element. And I'm only doing this because I want to say that the trivial topology is not the same as the discrete topology. That's pretty much always the case, unless x is just a point. So now I consider the identity function, but I will change the topologies. So I will take identity of x. Going out of x, I want this to be continuous. So here I can put the discrete topology to x with a trivial. This map is absolutely invertible. It's absolutely continuous because everything going out of the discrete topology is continuous. So this map is continuous and bijective. But its inverse map, which now goes out of the trivial topology, but the identity inverse, which is just the identity map going out of x to from the x with the trivial topology to x with the discrete, is not continuous. And why is that? Because everything here is open, but you have only two open sets here. And when you compute pre-image, you are not doing much. You're doing just the identity. Okay. Do you need me to write that? Is it clear that this is not continuous? Okay, so in contrast to the linear algebra case here, you could have a bijective continuous map where the inverse is not continuous. But this is, let's say, not a very satisfying example. I don't think it is. So now what I will do is very briefly go to my Zoom. So yeah, now the idea is we're gonna go back to the subspace topology or the induced topology. That's something we discussed in homework 1. And I want to do that mostly because I want to have a better example than this one. But not only because of that, because at some point I also needed to discuss that.
Are we saying for this that bijective is not as strong here as it is in linear algebra? You get things for free when something's when a matrix is linear transformation is bijective.
Yeah, you could say. Yeah, you could say that, but it's mostly like. Yeah, I don't know how to say that, but that's kind of what's going on. So a function being invertible is not really something that you can like extrapolate to the inverse function. Being continuous is not something you can extrapolate to the inverse function.
You don't need to check continuity in the inverse.
You need to check that here. And the reason is probably, so how you prove things in linear algebra, you can prove element-wise the inverse needs to be linear. And probably the main difference is being linear is something that you check element by element. It's like f of x plus y equals f of x plus f of y. But the inverse being continuous is something that you don't check element-wise, you check like subset-wise. And probably that's the reason why invertibility, continuity of the inverse is not for free. But yeah, I mean, the main reason is we have examples, but probably that's what's behind it. Okay, induced topology. So definition, this is not new, but I want to say this again. Definition 3, let's take a topological space X, and I will denote T of X, the topology of X. So topological space. And I'm going to take any subset. So the induced topology on a subset A of X is this collection of opens that's denoted by T sub A. Here I'm going to include, let's say, U subset of A, such that there exists some V in the topology for X, for which U is A intersection with VX, with V, sorry. So the opens in A are opens in X intersected with A. And you prove in homework 1, this is a topology on A. So in this case, if you endow A with this topology, we say A is a subspace. Of X. Not only a subset, we say it's a subspace because we're imposing this topology. So you prove this is a topology on A, and examples, maybe something I should have said before. Let's take X with to be the reals with the standard topology. And now let's take subsets A to be non-negative real numbers, and let's U be from 0 to 1. So what we have, let's consider on the induced topology on A. Let X to be reals with the standard.
Oh, consider, sorry, I can't.
Yeah, consider, sorry. So consider an I the induced topology. So what we have is, we have U inside of A, inside of X. So this U, probably you know this, it's not open in X. So U is not open in X. Because 0 is in U, but if you do negative epsilon, epsilon, that's not contained in U. Right? Because so 0 is an element, but U is not a neighborhood of 0. Because if you do negative epsilon, epsilon, that's never contained in U. However, U is open in A with the induced topology. Because I can just write my U as A intersection, for example, this open. This guy is open in the reals. So maybe you are not open in the big ambient space, but you can be open in a subspace. Okay, anyhow, that's just an example. And now, again, continuous functions relate to everything. And probably that's because that's the only way we have to relate stuff. So definition, this is not a topological definition. This is a set theory definition. If we have a set, so I don't have any topologies here. We have a subset of the set. I don't know if you've seen this before, but you had. I want to define the inclusion map, which is denoted usually by iota from A to X. Probably should be called iota sub A. Is just given by, I take iota sub A, I evaluate it at an element A in A. Inclusion shouldn't be doing much, and it's actually not doing much. It's A. And that's for any A in the set A. So this map is not the identity because the domain is not the codomain. Do you see what I'm doing? I'm just right. The identity of, for example, the identity of X.
A is not X.
Right. So these two things are not the same. So this cannot be the identity, but the rule that you are using is the identity.
But the little a's are in.
Only in A.
They're in X. The little a's are only in A.
Yeah, I don't want to. I cannot define iota for an element outside of A.
But isn't A subset of X and little a's are inside of big A?
Yeah. So every little a that I'm considering is an element in X, but here I don't want to consider any element of X, just some of them.
Oh, you're picking an X where A is not contained.
Oh yeah, it is. So each of these guys live inside of X, but there are more. There's probably more stuff in X. But this is not the identity because A is not X. So let's just say this is a way of, instead of writing this, having a function. That's all I'm having. Nothing too crazy here. So proposition, this should be proposition 4. I want to start with a topological space. So let's xt topological space. And let's take a subset. Let A inside of X subset. So before I state the theorem, if I take an open here, V in X, and I compute the pre-image under iota, what will I have? If I take, I don't need this to be open. If I take a subset V of X and I compute pre-image of V. By definition, this is all elements in A, such that when I apply iota, I get something in V. So this will just be A intersects V. And this is how opens in A look like if you let V be open. So the theorem is going to tell you if you have a topological space and you take a subset, then the induced topology, is the coarsest or smallest on A such that the inclusion map is continuous. And this is somehow telling you there is some universality about this induced topology. It makes sense to consider this one. And the proof will, of course, be an exercise for you. I mean, this is not going to be, yeah, it's going to be an exercise for you. But it's easier than the product one. So why is this function continuous when you consider the induced topology? Just because of that. And why is it the smallest? Also because of this. Okay, so I feel this is already explaining why this induced topology makes sense. This is a good explanation. This function, the inclusion, is very natural, should be continuous. Then you want to take the coarsest one for which that's continuous. That means you have just enough open sets. Okay, more set theory, definition. This is again just set theory. Let's start with the function. F from X to Y. I don't have any topologies here. And I will take subsets. A be a subset of X and B a subset of Y. Have you defined restrictions before? Restrictions of functions. Have you seen that before? Let's see. So one, the restriction of F to A.
Notice it's like all of the, there's something like all of the outputs that would be in A, right?
No, just restrict the inputs to A. You can
Let's
apply F to anything in X, then you can just restrict to A. So it's the function F restricted to A, that's the notation. And now it's function going out of A to your Y. And this is given by F restricted to A at an element A is F of A. And this is for any A in A. So this is kind of too complicated. I don't think there's too much going on here. I mean, it's mostly notation, but how do we express this more clearly? In other words, this F restricted to A is this composition. Go from A to X with our inclusion, and now apply F. And that's what's actually going on. So maybe I can say F restricted to A is just first do iota of A and then do F. And that's kind of why inclusions as functions make sense, because now you can define restrictions in a more precise way. So this is the first part of the definition. The second part will involve that B. But the thing is, you cannot always restrict to a subset of the image, of the codomain. You can only do that for some Bs. So in case the image of X is inside of B, we can co-restrict. That co-restriction of F to B is the map. So I know I use map and function with no distinction. Is the map. I will use this notation now. So this one is not a standard. The restriction notation is very standard. This one is not. F to the B, kind of. I will go out of X to B, And I will just use the same notation. So f to the b at an element x is just f of x, we are assuming is an element in B. So I'm not really doing much here. But notice, for this definition to make sense, I really need this. Do you understand what's going on here? Or do you want me to draw some pictures? Yeah.
Can I interpret the restriction from here?
Absolutely, yeah. The restriction case, I'm truncating the domain. And in the core restriction thing, I'm kind of, I know I don't need all values of y to express my functions, and I can just use less. Yep.
And you just explained it there, but so for the restriction, you're restricting all the inputs to values in A. For the code restriction, how do you describe it? Isn't it the same thing kind of, or how's it different? Are you restricting all the inputs to values in B?
Yeah, but it's not really that I'm restricting, but I know I don't need all of y to express my function f.
So what's the difference between restriction and code restriction?
Very different. In one case, I'm changing the domain. On the other one, I'm changing the codomain.
Oh, so, okay, I get it. One, you're only applying a function to values in A. The other one, you're only applying the function to things that land in B.
No, I'm assuming everything lands in B. So in the first case, I'm kind of reducing the domain. On the other one, under an extra assumption, I'm reducing the codomain.
Yeah, under the extra assumption, it's the same thing where it's like, yeah, like Edward said, here you're restricting this side, here you're restricting this side.
Right. But the thing is, you can always restrict the domain. You cannot always restrict the codomain. That depends on the set you have. Okay, so why I'm saying these things, because now we have a proposition . Five. So here, let's take a continuous map. So that means we have some topologies involved. The first statement here is if we have a subspace, that means a subset with induced topology, then the restriction is always continuous. And f restricted to A, which goes from A to X, is continuous. And the second part here is if we have a subset of the codomain and we can co-restrict, maybe I should say this is a subspace. Once again, that only means I'm taking the induced topology. Then the co-restriction f to the b, which goes from X to B, is also continuous. And you guess it, the proof for this will be homework. Usually when I leave stuff as homework, it's because you don't really need any very clever ideas. You just need to go through the definitions. So there is not much for me to explain in the proof, but it could be very, very helpful for you to like go through the proofs. So proof will be homework, of course. Yep.
When you're writing the restriction function, is that just f vertical line subscript, f vertical line subscript?
Yeah, I have my own LaTeX environment for that, but it's just Yeah, it's, you can do mid. No, sorry, you shouldn't do mid. You should do vert underscore or vert upscore. Okay, so why am I doing this? This is the last thing I want to do today. Example. Maybe it's too late. But what we'll do with this example, yeah, let me stop the record. So that will be today for, that will be it for today. We'll continue with this next time, but